Now we will move to forward to technical session.
It's always a privilege because Puthul I know from long time. Actually, I have this long CV of biodata what he has given me. But what I do is I will, Puthul, with the permission of yours, I will sort on your CV and speak certain highlighting what are the things they have been with you. So first of all, he got his PhD in physics from VNGU in 2010. Getting after PhD and serving in a science college, PT Science College, the most important thing what he has contributed to the science college is very, very important. Under his leadership, the science college has got, I think, NAC grade, A plus grade under his capacity of as a PT Science College. So we congratulate PT Science College for getting the A plus grade under his guidance. As well as he received a status College of Potential for Excellence, that is CP by UGC, New Delhi, with a grant of rupees 1 crore, right, which is commendable in that concept. And college also received a RUSA 2.0 under a component of 9 by MHRD with a grant of 2 crore rupees. And this is something which I always say that the Puthul can do it and his team can do it. So congratulations Puthul and his team for doing that commendable job. And this college was confirmed autonomous college in 2023 by UGC. And that is why now he is an autonomous college. So they have got a license to do what they want to do and they want a license to do what they want to grow now. So we look forward to your potential applications as well as commendable jobs in your science college. And I would hope that will make us proud by being a physicist as well as being an administrator. Now I welcome and I will ask you to go ahead with your lectures. Thank you, Puthul.
Thank you, Padre Sahib, for a generous introduction. And I would like to thank Puria sir once again for, on one phone call he agreed to organize this event, which is the first regional council, first annual meeting of the regional council, annual convention. So I would also like to express my thanks to all my, EC members of RC7 and especially Vinod Kumar sir, who has been, constantly guiding us, prodding us, applying periodic force so that, we all remain in resonance and, we come out with some wonderful, events for IAPT RC7. So thank you. I hope I'll be able to engage you all in this fascinating world. And the title of my talks tells it all. It is Platonic Love at a Distance, Quantum Entanglement. So these are the you can say heroes of this entire discussion that we are going to organize. Of course, there are many others who have contributed, but these are the people who have contributed the most or who have made notable contributions. So we will be discussing those things during the course of the time. So as Vinod Kumar sir said that we are celebrating, IYQ 2025. So it's an international year of quantum science and technology, and it coincides with 100 years of the discovery of quantum mechanics. So friends, we know, so it's a time for us to reflect upon what we have achieved till date, and it also gives us an excellent opportunity to look forward to what else we would be seeing in future. So this IYQ primarily aims at highlighting the achievements of quantum science till date and what is in store for us in future. So it's 100 years of quantum, and we call it just the beginning. because we are almost at the cusp of the second quantum revolution. So I'll be discussing a few points in that regard during my speech or presentation. So I start with these three masters who have time and again we call their names whenever quantum physics is discussed. So these are the statements. One is by none other than Niels Bohr, who says that those who are not shocked when they come first across quantum mechanics cannot possibly have understood it. This is another great master of all, Richard Feynman, saying that I can safely say that nobody understands quantum mechanics. Now this slide also is very important for any speaker who speaks about quantum mechanics. Because if you ask a difficult question, I will only refer Feynman's statement. Nobody understands quantum mechanics. So don't ask me difficult questions at that. And the third master of all, the theory yields much, but it hardly brings us close to the secrets of the old one. In any case, I am convinced he does not play dice. So this statement of Einstein, in fact, is something which we'll be using, and this sets the tone for the entire discussion. I have to Marupal pen. Just 1 minute. I have one correction in that I have not. This file is not the correct one. Just 1 minute. See, all my files are entangled. So
you sent some message from here.
But you have to carry them. Both are entangled. Correct. But he has to carry the information.
That is the only difference.
That is what he thinks actually.
Extremely sorry, I apologize. I changed few things in the morning, and then my own laptop is not connected. So I'm sorry for the delay, but I would like to comment on the last statement of Einstein. Einstein was not happy with the probabilistic nature of quantum mechanics, and in fact, in the later stage of his life, he did not question the results of quantum mechanics, but in fact he questioned the ideas which lead to these results. So that is the key for the root cause of all modern quantum technologies that we believe is going to shape our future. So that's why I have particularly mentioned the statement of Einstein. And Einstein, every time we know these famous Solvay conferences debates in which Einstein used to question and especially he targeted the uncertainty principle, and he came up with various Gedanken experiments to challenge, to bypass the uncertainty principle, and Bohr was equally up to the task. Einstein would ask a question in the evening or maybe during the discussions in the day. Whole night Bohr will think about those questions, and next day morning Bohr will come up with an answer. So this debate, in fact, about the true nature as a theory, what a theory should be and its true nature, was always questioned by Einstein. So for all the students, you should be very clear, Einstein never questioned the results that we get out of quantum mechanics. See, because he knew that quantum mechanics is one of the most successful theories. These theories its predictions have been verified to unprecedented degree of accuracy. So there is no theory till date which has been verified to an extent that quantum mechanics is. So there was no question on the part of Einstein he said that this particular theory is not the final word as far as description of nature is concerned, and that led to this particular idea of entanglement and everything. So I am convinced he does not play with dice. So that's the starting point of the discussion for today. So I call it the genesis of quantum information. So in 1935, as I told you, Einstein questioned once again. He attacked in 1927. There were debates between Einstein and Bohr, and nearly 8 years later, he attacked quantum theory once again. In those debates of Solvay conference, Einstein always took one particle. Now he says, suppose you have two particles, and then this two particle thing and interpretation of quantum mechanics is something which he attacked. And this is the famous paper which is called EPR paper. And Einstein and his two junior colleagues, they put forward a question. And the question was, is it possible or necessary to explain the probabilistic character of quantum predictions by invoking a substructure or a supplementary underlying level of description? So the level of description that quantum mechanics gives, is there, it is any substructure, sub-level of description which would make it complete, so to say. So they question the title of the paper says it all, can quantum mechanical description of physical reality be considered complete? So completeness of quantum mechanics was challenged by EPR. Curiously, if you look at both the slides, Bohr replied to that. So Bohr replied, see, Einstein's paper was in May, physical review. Bohr's paper was in October. So nearly 6 months later. And look at the title of the two papers. It is the same. Okay. So Bohr replied to Einstein's probing of quantum physics or quantum theory, and he says that the theory is complete. Einstein is saying theory is incomplete. We'll come to that later on, why he feels it is incomplete. But at least Bohr offered a rebuttal to Einstein's idea, and he says no, the theory is complete. In 1935, another great physicist, he also enters into this so-called debate between Einstein and Bohr, and he says he realizes that there is one particular property or trait of quantum mechanics which makes it unique. So he says quantum entanglement is the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. So the word entanglement or quantum entanglement was coined by Schrödinger in 1935, and I have read that paper. I want all the students should read this paper. In this paper he says, if you permit me, I will add more to the confusion rather than the solution. So this is what he said. So he said, I am really confused or fascinated by this word of entanglement, the behavior of entangled particles. And finally, this debate between the two giants, Bohr and Einstein, was once again looked at again nearly 30 years after this paper of 1935. That was in 1964. John Bell decided to look at it again, relook the paper, and he comes up with a solution to this debate between Einstein and Bohr. So my talk will be aligned with this. And this is another great gentleman who knew the importance of quantum entanglement, and he, in fact, he had this, you can say, at times you find it is prophetic in his ideas, and he knew the importance of quantum entanglement. He said quantum entanglement is much more, and he wrote a paper simulating physics with computers using quantum entanglement. So the first idea of quantum computers was originated, or rather you can say it was given by Richard Feynman. So at the what connects all these four papers is this wonderful idea of quantum entanglement, and it is at the core of quantum information. The next the next quantum revolution that we are looking at. So I would like to, in my talk today, I would like to say something about quantum entanglement and the technologies that will emerge out of this idea of quantum entanglement. So these are the few terms that we will be using during the discussion. So one is reality, which is existence of an objective observer independent world, and it is often related to the deterministic values. Determinism, causality, locality. So something which I do here will affect only my neighborhood or will affect region which is very close to where I am. So for example, suppose I am speaking right now, not suppose I am actually speaking here in Patan. Does it have any impact on what is happening in USA? So locality means it impacts at a very local level, and hidden variables, I'll come to that. So quantum description of any system, as you all know, is the state of the system is described by this wonderful object named wave function, and the time evolution is of course the famous Schrodinger's equation. We are of course restricting ourselves to the non-relativistic case, and it's a linear equation, and as a result law of superposition holds. So that is the key for this idea of quantum entanglement. So a single qubit, Puriya sir just mentioned that we will be now having qubits, and we will have various technologies based on that. So a qubit description can be obtained with the help of what is called a Bloch sphere. I think students may be knowing that. So it's a sphere of uniform radius because this is, and if I say this is the direction along which I am measuring the spin or any property of a quantum particle, in this case particularly spin. So if I take this as my z-axis, then the spin of electron can be aligned either parallel or anti-parallel. So the wave function, if I parameterize this wave function in terms of spherical coordinates, then I will get it as cos theta by 2 plus I sine. So phi is nothing but the phase vector. So I have phi, which is a variation of angle along perpendicular to this equator, and you have the two axes x and y. So z-axis, I am calling this vertical axis as z-axis. So in terms of these parameters, your wave function gets described like this. Now what happens if I mix these two? So one is spin down state and another is spin up state. So a law of superposition holds. It's a linear equation. So what will happen is you will get a superposition state of which is a combination of these two, and any point on the surface of the sphere, it represents a pure state. So it's called a pure state, and at any distance other than that, means if the magnitude is less than 1, then it will be called a combination or an integral state. I'll come to that later on. So quantum mechanics says that usually all particles are in a superposition state, and it is the act of measurement which will force the particle to get into a particular state, which is often called as collapse of the wave function. So measurement will always, in this particular case, will give me either spin up along z-axis or spin down along z. So I am calling it always +1 or -1. And the probability of this happening, quantum mechanics says it is 50%. You measure the spin of a particle, you will find either it is spin up or spin down with 50% probability. Now interesting thing happens if instead of one particle I have two. So instead of 1 qubit, say I have 2 qubits. Now what is going to happen? Now if you have 2 qubits, then the state vector, see initially if you have single qubit, the state vector requires two vectors, two basis vectors to define. Now if you have 2 qubits, you will require 4 basis vectors. So your Hilbert space now becomes 4-dimensional, and you can have states which are called product states. So if your total wave function of the two particles is product of wave function of individual particle, then it is called a product state, and each can be represented with the help of its own Bloch sphere. But quantum mechanics, since it's a linear superposition principle holds, combination of these two is also possible. So you may have what are called entangled states, and these entangled state of an means combined state of the system cannot be represented as product of two individual single particle states. Then such states are called entangled states. So for example, I have say one qubit, another qubit, and our law of superposition says that the net will be sum of the two, and my total wave function of the system can be described as it's a 4-vector system, it's a 4-dimensional Hilbert space, so it will be 0, 0, so spin up, up, or 0, I may call it minus, then two particles having spin down, one spin up, another spin down, spin up, spin down, and both spin up. So your wave function will be combination of all these four possibilities, and this in terms of A1 and A2 I can write it like this, and then I ask a question to all the students, is this state possible or not? A00 plus alpha 00 plus delta 11. You will find for alpha 00 and delta 11 what is required, beta is 0 and gamma is 0. Now beta is nothing but A1 B2 and gamma is B1 A2. So any of these have to be 0, and if that is the case, your alpha is also combination of A1 A2 and B1 B2. So if A1 and B1 are 0, then this particular state cannot be expressed as sum of two individual states, and this is precisely what is called an entangled state. So entangled states are unique states which are allowed because of the linearity of the Schrodinger equation, and these are the states where the state of the total system, combination of two qubits, cannot be expressed as product of individual qubits. So these are entangled states. So EPR, the paper which I showed earlier, it asked a very important question. Once again I stress here, EPR did not question the results of quantum mechanics, it asked particular question about certain aspects of quantum mechanics. For example, it says that what does it mean for a theory to be complete? Then EPR gives two definitions. One, a theory is complete if every element of the physical reality must have a counterpart in the physical theory. That is one. And if without in any way disturbing the system, we can predict with certainty the value of a physical quantity, then there exists an element of reality corresponding to this physical quantity. Now these are the conditions which are sufficient and necessary for a theory to be complete. Under this condition, EPR tried to evaluate an entangled state. So let us see. Suppose we create a two-particle quantum state. So that quantum state is HTTH. So this is particle 1 and the second one is the measurement of particle 2. So the particles are then separated. So initially you create the particles and then says the two particles are individually separated to a large distance. So say they are separated. So I have now a place where I may say an observer named Alice. So one particle is at the end where Alice is sitting, another particle is at the end where Bob is sitting. Now if Alice can measure, Alice measures it, she can measure either H or T, Bob can measure H or T. So, and there is no restriction, I can take these two particles to the two ends of the universe. They can be, in fact, they are infinity or separate or a very large distance. Okay. So now suppose Alice decides to measure the state of particle 1. So quantum mechanics says the probability is 50%, so Alice will either say H or T. So once it measures, then the total momentum, initially the net momentum was 0. So if this measures say H, or you may say momentum plus 1 or spin up, then you will automatically deduce that the other particle has spin down. So if Alice makes the first measurement, quantum mechanics tells us that there is 50% chance that the particle 1 will be either in state up or state down. Now, as soon as we measure the state of particle 1, we are in a position to conclude the state of particle 2, which is at very large distance away from us, and mind well, we have not carried out any measurement on particle 2. What we have measured is the state of particle 1. So we are able to infer about the state of particle 2 without actually measuring it, is what EPR argues. So in other words, we can determine the state of particle 2. Einstein says that how is it that if I measure something at particle, means if Alice measures something, a particle which is in almost at a very large distance away, how its spin is getting affected by measurement of Alice here. So if Alice, it's 50% probability, so if Alice measures the spin of particle 1 and finds that it is spin up, Alice will automatically conclude that spin of Bob is down. If Alice measures spin down, then Bob's spin will be spin up. So even if Bob measures that spin, he will always find it spin up. So what it means is that the measurement that Alice makes is somehow affecting the spin of Bob. So if Alice measures up, Bob's spin is down. Alice measures down, Bob's spin is up. So spin of Bob appears to be decided by the measurement carried out by Alice, and since they are at very large distance, they are light years away, so there is no question of communication between them. So there is an effect which is getting transferred from Alice to Bob. This, Einstein says, is something which is unacceptable under the definition of those when a theory is complete. So this is what it says, that spin of particle 2, if it is spin down, so it must be an element of reality, and if it's an element of reality, then quantum mechanics says that you will come to know about element of reality only by an act of measurement. So here EPR argues that I have been able to find out the spin of particle at Bob's end without actually measuring its spin. So that means in that sense he says that the theory is incomplete. So Einstein called it spooky action at it. Einstein was absolutely unhappy with this idea. Something you do here affects something which is light years away. So locality, he says, is being violated, and any theory should be local. And what you do here should not be affecting it there, at least at a speed greater than the speed of light. Here what you find, Alice measures up, instantaneously Bob's spin becomes down. So Einstein says that it violates the law of special theory, that no information can be traveled, nothing can travel at a speed greater than the speed of light. And that is the question which EPR posed. And when Bohr saw this paper, he was in a state of shock. Means he spent 6 months dreaming daily, thinking about this problem which was posed by EPR to come up with an answer. And that the answer that Bohr came up is also not very convincing. And as a result, we find there are different kinds of interpretations of quantum mechanics. There are many worlds interpretations. So people, even after 100 years, we find that the results of the predictions of quantum mechanics work out very well. But what, the psi, the interpretation of psi is still, lots of it evinces, mixed response from different people. So that is what I said. EPR concluded that QM does not predict all elements of reality, and as a result it is an incomplete theory. Once again I tell you, EPR did not doubt the results of quantum mechanics. So EPR says that to make the theory complete, there must be few variables present in the theory which are not known to us. So we say these are hidden variables. Now these hidden variables establish the connection between the two particles, And with the help of these hidden variables, we should be able to predict exactly the outcomes of measurement at Alice and measurement at Bob. So Bob's spin is connected to the spin of particle at Alice because there are some hidden variables which establish connection between them, and these are not known to us, so they call it hidden variables. So idea of hidden variables was put forward by Einstein in the last line of his paper. Maybe a theory of hidden variables will be able to make QM a complete theory. So when Einstein comes up with this paper, this is the famous New York Times headlines: Einstein attacks quantum theory, scientists and 2 colleagues find it not complete, even though correct. So this was the headlines in New York Times, and in fact one of the co-authors, Podolsky and Rosen, I think Podolsky in fact leaked this information to press, and that's why New York Times came up with this headline. And Einstein was not happy with Podolsky for bringing it out. And in fact, Einstein, I've read somewhere that he never then interacted much with Podolsky because of this. He was very unhappy that you give the idea of the paper before it is getting published. So anyway, the important thing is, since 1935, as I told you, it was John Bell who decided to relook at the quantum or EPR paper in 1964. So from science point of view, for 30 years it was nearly, this EPR paper was a kind of not in the dustbin, but many people did not pay much attention to it. What is the reason? The reason is physicists of the time adapted to the strategy: shut up and calculate. You don't worry what the philosophy, what the theory should be. We know that theory gives us correct answers, so don't worry about that. It is for old people. Sorry sir, I don't want to mean that, to think about such problems, but these, we let us work out the results of quantum mechanics and it works. So why should we bother about what is the philosophy, theory is complete or incomplete? It works. So shut up and calculate was the attitude of most of the physicists at that time. And this is important. Sidney Ryder calls EPR paper as sleeping beauty because it slept for nearly 30 years. Nobody took it not very seriously, but nobody cared about it because results of quantum mechanics match with experiment. So it was only in this is what I call it as into inverted comma dark era of quantum mechanics. See, this is none other than Pauli. What he says: one should no more rack one's brain about the problem of whether something one cannot know anything about exists at all. Why do you worry whether the theory is complete or not? It gives us the right result. Then the ancient question of how many angels are able to sit on the point of a needle. We should rather concentrate on getting the answers. It works very well. Don't bother about it. This is what Pauli is saying. And Leon Rosenfeld, the person who was working with Bohr for a long period of time, this is what he says: I need not tell you that I regard your hunting hidden parameters as a waste of your talent. I don't know either whether you should be glad or sorry for that. This is what Rosenfeld told John Bell when he, in 1964, when John Bell, wrote down that paper, which is now at the root of the entire quantum revolution. So he said, young fellow, you are very smart, I appreciate that, but thinking about these problems, you are wasting your talent. So this was something John Bell faced in the early phase of his career. So what did John Bell exactly do? He showed that local realistic theories. So what are local realistic theories? A realistic theory is realists believe that world exists out there independent of your act of measurement. There is one famous quote by Einstein: does moon exist only when I look at it? So existence of world is independent of our act of observation is what our intuition tells us. So this is what every one of us believes. There is moon irrespective of whether I am looking at it or not. But quantum mechanics seems to imply that any observation that you make brings to light the reality. So it's an observable driven reality. You cannot say world exists out there because you cannot define a superposition state, and that's why only your act of measurement you define the state of the system. So this is something where John Bell, he came up with a mathematical inequality to show that such local realistic theories, local theories means theories which no faster than light communication is possible, and a realistic theory, it is incompatible with quantum mechanics. This is what he said after analyzing the EPR paper. So what actually Bell did was to turn a pure philosophical debate between Bohr and Einstein about what theory, whether it is complete or not, into a mathematical form which, with appropriate changes in the measurement or appropriate designing of the experiments, will help us separate. So now the Bell's contribution was, he says that this is the inequality, I'll get to that, but this is the inequality, a local realistic theory or local hidden variable theory will obey that inequality, and if it is quantum mechanics, then it will not obey. So that means now you have a kind of a device, a kind of a method to check whether the argument, who wins the argument, whether Einstein is right or Bohr is right. So that is the greatest contribution of John Bell. And that's why Bell's theorem is the most profound theory, or most profound discovery of science. Is Henry Strepp saying that. So what is Bell's inequality? How we can separate out between a theory which is hidden, theory made up of hidden variable, local realistic theory, and quantum mechanics. How will you be able to separate out? So suppose I have a local hidden variable theory, I am calling it LH, a local hidden variable model, where the spins of the particles are properly correlated. If this has spin up, this has spin down, this has spin down, this has spin up. So if you have a perfect correlation, what you will find, if Alice makes measurement of one as down, the other one will be up, up, down. So this is a perfect correlation. Okay, there are some variables which are present in the system which ensures that this correlation is established. I am calling it perfect correlation. Now what Bell did, instead of measuring along x, measuring spin along x or y two directions, he said, why not measure the spin of the particle along a third direction other than x and y. If it is perfect correlation, then you will find you measure it along x, Alice measures +1, Bob will measure -1. If Alice measures +1 along y, Bob measures -1. So it is a perfect correlation. Now Bell says, let us measure it at an angle other than x and y. So he says, suppose I have a direction, say q, and I want to measure the spin of the particle around q, which makes an angle 45 degree with respect to x-axis. Then in that case, these are the 8 possibilities that he will observe. Spin along z plus, then you can have x plus, and you can have, so all the spins along all the 3 directions, 3 spins along 3 directions can be positive, along one positive, along another negative, third positive. So likewise you will have 8 possible orientations of spin that can be measured by Alice when Alice measured spin of particle 1 along 3 directions. I hope you understand this. Now what happens? Suppose these are the possible events of Alice's measurement of spin 1. Now if you have a local hidden variable theory which ensures perfect correlations between them, then look at the probability P z plus x plus. So that means Alice measuring z plus along z direction, plus 1 along z direction, and what is the probability that Bob will measure x plus along his x direction. Okay, So what are the possibilities? E3 and E4. See, here minus came because the spins are and they are correlated. Ek no spin 1 hoy to bijano spin down. So if I have to find out probability Pz plus x plus means Bob's spin measurement should be x minus. So E3 plus E4, and what are the total possibilities? 8. So the probability becomes E3 plus E4 by 8. Similarly, what is the probability of occurrence of Z plus Q plus? Students, Z plus Q plus. So this is Q plus. So spin of Bob must be Q minus, because if Alice measures Q plus, Bob has to measure Q minus. So Z plus Q plus will be E2 plus E4 by 8. Q plus X plus E3 plus E7 by 8. So PZX plus is less than equal to PZ plus Q plus PQ plus Z plus. Is it not? So effectively you find that E3 plus E4. So it is E3 plus E4 is E2 plus E4 plus. So these two get cancelled. So this is 1. So E2 plus E7 is greater than that. So what Bell said is that if you have a local hidden variable theory where you have correlations established through hidden variable, if Alice measures Z plus, Bob will measure Z minus. Alice measured X plus, Bob will measure X minus. Alice measures X, what quantum mechanics says, if Alice measured X plus, Bob measures Z minus, Alice measured X plus. So if the axes are same, quantum mechanics also says the spins will be opposite. But if the axes are different, means Alice measures along X and then measures along Q, then the correlations between Alice's measurement and Bob's measurement are not same. So you find that local hidden variable theory will say that Pz plus Q plus is 1 by 4, and quantum mechanics predicts that it is sine square. So because the angle is 45 degree, it is sine square theta by 2, and you find that at all these values, all these angles, you find that quantum predictions match with those of local hidden variable theory, and these angles, they mismatch. So see, Einstein and Podolsky did not think of a situation where the measurement is at angle other than along 90 degrees. Okay, so Bell's contribution was, he said you should measure it along the 3 directions and then try to find out what are the correlations in the spin that are observed by 2 particles. And he says that that is where you will find this is 25% and this is 14.6. So blue curve represents quantum mechanics predictions and red is the straight line which is local hidden variable theory. So he showed that if you have a quantum theory predictions will be always less than the predictions of LMB. So the inequality will be violated by quantum mechanics, while if you have a local hidden variable theory, the inequality will be satisfied. So now the question was to measure the spins at these angles. That's the most difficult part. So first such measurement was made by American physicist John Clauser, and that was in the year 1972. So it took us nearly 8 years to come up with the experimental setup which will help us measure spins or polarizations of light at different angles. And he used pile of plates. I will not get into that, but he somehow showed that, you know, the observations which were made by Clauser, they in fact showed that quantum mechanics violates Bell's inequality. The problem with Clauser's experiment was there were various loopholes present in the experiment. Loopholes means it provides a theorist to say that the observations which are made by experiment, there are some loopholes in that. In the possibility there may be some communication between the 2 detectors and so on and so forth. I will not get into the details of that, but his experiment at least was a step forward in the right direction. So it took 8 years, and he is the first generation of scientists who manipulated. See, nowadays we can observe and manipulate photon. So these are single photon experiments, and because you require 2 qubits or 2 paired particles, So you require 2 single photons. So to have a technology of developing or creating 2 photons was first time, developed by Clauser, and this is what is called step down of 2 photons being emitted and cascading down of photons, I think. So and then they showed that this is true up to 1 standard deviation. So the error was up to 1 standard. So that was not enough to conclusively say that quantum mechanics violates Bell inequality. So this was the next generation of experimentalists, and Alan Aspa and he once again further improved the experiment which was of John Clauser, and see, it is 1982, so nearly 10 years. It took him 1 decade to come up with an improved experimental setup which will be able to tell him convincingly that whether quantum mechanics violates Bell inequality or not. So I will not get into that, but he showed that quantum mechanics violates Bell inequality. Now the order of 13 standard deviation. So the accuracy of his result was improved tenfold as compared to Clauser's experiment. And I think Vinod Kumar said, if I am not wrong, theoretically we say anything beyond 5 standard deviation is an accepted result. So this is 13 standard deviations. It was quite convincing for scientists to believe that yes, quantum mechanics violates Bell inequality. And then he further improved, because there were always skeptics. There are skeptics whenever experimentalists come up with results. Theorists will try to figure out some loopholes in your experiments. So there were people who questioned Aspa that the connections between the 2 detectors, these 2 detectors may be somehow establishing connection between them. We don't know why, but there is still a possibility. So what he did, he could change the orientation of the detectors after photons left the source. So once the 2 photons which are along their direction, 2 experimentals, Alice and Bob, once the 2 photons start moving towards the detectors, after they are emitted, after they are created, you change the orientation. So photon doesn't know in which direction his spin is going to be measured. So he improved that, and once again he found that yes, quantum mechanics violates Bell inequality. So finally, I would like to point out how over the period, Upadhyay sir, experimentalists improve. See, Clauser's experiment took him more than 100 days to come up with the result. And using Aspa could come up with the result in 100 seconds. So in 10 years, the detector efficiency and everything got improved, and more conclusive evidence was obtained. So finally, in this debate between Einstein and Bohr, it appears that quantum mechanics seems to have won there. Excuse me. So the entangled photon remain mysteriously bound to one another. So that's why I am calling it Platonic love at a distance. Once they are created, once they are entangled, wherever they may be in the universe, they continue to remain entangled. So, and there is a mystery associated, we don't know why, but that is how it is. And when you make a measurement, the wave function collapses, and immediately, the spin of other particle changes. And the properties of the entangled particles, you can say, this is what is famous statement by, once again, Schrödinger, that the total is more than the sum of the individuals. Okay, so sum of the individual properties of the particle, the total is more than that. So the properties of pair of entangled particles are more than that. Usually for entropy we say that sum of the entropies of individual systems is equal to the sum of total sum. S is equal to S1 plus S2. And entanglement is a global property. So that means, these 2 particles cannot now be defined as 2 individual particles. They would be always defined as 2 entangled particles. So they will be defined by a total wave function, each individual particle loses its identity the moment it gets entangled, and that is the root. That is the root of the current quantum revolution. This idea was further used by Anton Zeilinger. Now he is the third generation. You can look at his paper. His paper is in 1998. So from 1982, nearly 16 years later, he further improved Aspa's experiment and accuracy, and he found that quantum mechanics violates band inequality to 30 standard deviations. Not only that, he went further. He used this idea to for the first time demonstrate what is called quantum teleportation. So that was also one of the contributions of Zeilinger. And friends, in 2022 all these three gentlemen got Nobel Prize in Physics. So finally, entanglement as a driving force. See, the current technology, Professor Vinod Kumar asked me to speak something about it, although I am not an expert in that, but I will make an effort to do that. So there are three main technologies which are driven by quantum entanglement. They are quantum computing, quantum cryptography, they are computing to a certain extent connected, and quantum teleportation. So quantum computing, so instead of classical computers which have bits, we will now have analogous qubits, and these qubits are entangled, and we believe that since they are entangled, you do something here, instantaneously gets affected something there. So the transmission connectedness is almost instantaneous. So we believe that with the help of qubits, if you can manipulate qubits, then the speed of computers will become astronomically large as compared to what we have today. We are ruled by Moore's law, which says that the density of atoms per square meter cube or centimeter cube of the chip. Now we have almost reached that saturation. So we find that quantum computers may be the next generation, and this is precisely what in 1985 Richard Feynman wrote in one of his articles, or this paper. Now, entanglement cryptography. The problem is that, see, we are in a world where everything is nowadays digital. We make use of these OTPs, and we believe that our messages are all, safe. In the sense that I communicate with someone, I expect that there is no Eve or eavesdropper. You can interfere and intrude into the communication. Now, our current computers, I think, if I am not wrong, they are based on the keys are generated with the help of prime numbers, and you multiply two prime numbers, and to get or to factorize these prime numbers is difficult. So even if I have a supercomputer, it will take me years to break a code of large prime numbers. So that's the essence. Means I'll have to spend lots of energy. My supercomputer also requires energy. And to break a password of my account, which has not more than lakh of rupees, okay, what is the fun someone will have? It's not easy to break. But if I have quantum computers which are exponentially faster, then that process of breaking a code will be reduced to manageable amount. So that is where the next challenge for us is. So what to do? We have to somehow change our current encryption method, because we believe that if quantum computers come, all our current methods of encryption, they may be challenged, there may be question mark on that. So that's why the next point is, we are thinking of having quantum key distribution. Means keys, the encryption is based on qubits and quantum ideas. So this is what it is. If you have a quantum key distribution, so you have Alice and Bob, and you create a state is prepared, that state is communicated to Bob, so they are entangled, and so you create entangled particles, you send it to two ends, Alice and Bob, and Alice, through an authenticated classical channel, can communicate to Bob the basis vectors on which she has created a state. Once Bob knows that, he can recreate, or so the way she has encrypted the message, he can decrypt it. So he can get back the original message, and this Eve, about which we are all worried, if he tries to intrude with any of this quantum state, then immediately it will collapse into one of the states. It will lose its entanglement, and Bob will come to know that someone has intruded, someone has done something with the code. So that is the beauty of this quantum key distribution, which we believe will be the next method of encryption in future. And finally, I'll say something about teleportation to the students, young students. You were not born when this famous series, Star Trek, was beamed across the globe. I was one of those young kids who were fascinated by this famous Starship Enterprise. And there was always one quote, or rather Captain Kirk, who was the captain of this Starship Enterprise. He used to always say, "Beam me up, Scotty." So Scotty was, Scott Montgomery was one of the scientists. This Captain Kirk used to go to various planets, and when he wanted to come back to the starship, he will say, "Beam me up." So he was teleported from a planet to the starship. So this is a science fiction idea. Now, can we actually in practice have something similar? So we have quantum teleportation. Will we be able to teleport an object? Maybe humans. So this was quantum teleportation was carried out, an experiment on quantum teleportation was carried out by Zeilinger. Zeilinger says, if I create an initial state, so I have a nice cartoon for that. You know, Alice has a yellow photon, say, and Charlie has a pair of blue that are entangled. Now what is going to happen? Charlie sends one to Alice, shares an entangled photon with Alice, and one to Bob, and who stores it in his crystal memory bank. So you have nowadays, digital banks, academic credit banks. Similarly, you will have memory banks. And Alice and Bob relationship is cordial but somewhat distant. This is love at far distance. And as the blue photon Alice received collides with her yellow photon, she measures the event and learns that the state of her photon has been teleported to Bob. Alice measuring the event affects Bob's faraway photon, changing its state. However, Bob can't determine that his photon has changed until Alice sends him 2 bits of information over an optical fiber. Because see, Alice has done something. Unless Bob measures, he will not be able to say. So for him to measure what I have done, Alice has to send a signal to Bob to tell him that, you see, I have measured blue photon or this photon along this particular direction. So Bob will carry out the measurement along that direction, and then you will find that this information of an entangled photon here is received by Bob there. So for quantum teleportation, this classical channel is mandatory. That will prevent any faster than light communication. So the question is, can we communicate can two objects communicate at a speed greater than speed of light? When I say when I measure spin, Alice measures spin 1, instantaneously the spin of Bob becomes spin down. So it appears that this is affecting that at instantaneous speed. Now, is it faster than light communication, which is not allowed by the theory of relativity? Then the answer to this question is that the entanglement itself does not transmit information. By itself it is not transmitting anything. It is, we conclude that if this is spin up, that has to be spin down. So it only establishes correlation between entangled states. Up है तो down है, बराबर. But there is no information has passed from Alice to Bob. So the classical communication step is necessary to complete the teleportation process, and this step is bound by the speed of light. So no faster than communication is possible. So without classical information, the receiver cannot reconstruct the original quantum state. So no useful information is transmitted faster than light. So this is the timeline from 1935, 1964, 1969, 72, 82, 2017, and now we are at 2022. We are at the cusp of the second revolution, because the process through which we will treat, or the physical principles with the help of which we will process the information, there is a change in that. Classically what we were treating, and now we are trying to treat information quantum mechanically using quantum entangled particle. So the physical process itself has changed. So there is a paradigm shift in the way we will be treating or carrying out quantum information. It will be completely different from what we have been doing till date in classical information. So finally I conclude, designed to reveal incompleteness of quantum theory, EPR eventually led to experimental results that instead reinforced the theory's most mind-boggling text. So it questioned the theory, but in fact that question is at the root of current quantum technology. See, I find that there is a fad, there is a trend. Everyone says you have to do research which is useful to the society. For them, this is a classic answer. The question was asked about the completeness of the theory. They never said whether it will be applicable to the students or not, or applicable to society at large or not. So research is not simply, we should not be concentrating only on, what is the applied part of it. Anything that you do, it will have some consequences, effects, some usefulness sometime in future. So the question was asked in 1935, we are bearing its fruit in 2022, and maybe the next generation will be there to see the development of quantum computers. Maybe I don't know whether I'll be live long enough to see that. Nature, it seems, is inherently non-local, and in the words of Einstein, nature is spooky. The root of today's quantum revolution, that John Bell's 1964 theorem, showing that quantum mechanics really permits instantaneous connection between a far apart location. So his inequality, his idea that quantum mechanics permits this, is the root cause of the technology that we are developing today. So quantum technologies hold a promise to revolutionize industries, from computing to cryptography to healthcare and logistics, by solving problems previously deemed impossible. So finally, once again, all the talk was centered around Alice and Bob. So I would like to finish it on a lighter note. See, this is what Bob is telling Alice. What can you see now in the quantum world? Alice. Oh Bob, it's looking spookier than ever, is the response. Oh Alice, you are the one for me. So that is when I was 18, I felt that. But Bob, in a quantum world, how can we be sure? Is the answer. What we are sure of is the conclusion of my talk. Thank you.
Here that I was a good speaker, and he proved that he is better than me. Any questions from anywhere? I only understood physics community should be entangled wherever you are. Right? One thing is. So we are globally entangled, and I believe that we are not like Bob and Alice asking the last slide what he has asked the question. Right? We should be one. So thank you, Pruthul, for a nice and very, very informative, nicely narrated, nicely connected, and taking the journey from last 35 years. We should not worry about what the importance in societal importance to the research point. I do agree with that, we should do the research, but what I also agree with that is the Bell inequality was not taught properly by an experimentalist, by a technician, by a technology people. It should not be proven even till today. So we required all together to work And that's why I told we have to be entangled, not only the physics, as a science we should be entangled rather than as a physics to be entangled. Thank you very much for giving me this occasion to speak for the chairman. Thank you very much.
I would just people who have played a very important role in whatever I am today. So I once again bow down to you. Thank you so much.
For the second technical session. In second technical session, I am hereby requesting Professor K.N. Joshipura sir to chair the session. And the speaker is Professor Vyas sir. And if anyone wants to ask any question to Putul Desai sir, okay, yeah, feel free to ask the question. Yeah, please.
Entanglement के बारे में बोला तो
Hello.
I say you can speak.
Audible?
You are audible.
ओके सो आपने क्वांटम एंटेंगलमेंट के बारे में बोला तो वो फिजिक्स फर्स्ट ईयर या सेकंड आई थिंक थर्ड ईयर बिटवीन फर्स्ट टू थर्ड में ये क्वांटम एंटेंगलमेंट आई थिंक से नहीं आता है तो मैं साइड से बोसन्स एंड फर्मियंस के बारे में पढ़ती हूँ तो मेरा फर्स्ट क्वेश्चन था जब मैं आपने फर्स्ट स्लाइड पे दिखाया अप एंड डाउन के बारे में तो जब स्पिन का डेफिनेशन ये होता है कि एक फिक्स पॉइंट से जो भी मतलब जितने भी डिस्टेंस पे जो भी पार्टिकल्स है वो अगर फिक्स पॉइंट के अराउंड कर रहा है तो हम उसे स्पिन का डेफिनेशन देते हैं जब आपने अप एंड डाउन का बात की इलेक्ट्रॉन्स एक फंडामेंटल मैटर होता पार्टिकल होता है तो वो खुद में स्पिन कैसे होता है वो फर्स्ट क्वेश्चन है कि वो स्पिन लाइक आई डिडंट अंडरस्टैंड कि वो स्पिन कैसे उसमें मोमेंटम होता है
No, it's an intrinsic property of just like charge.
और डिटेल में मैंने पढ़ा पर मुझे
It's not actually spinning about an axis. You don't see
That you read an American Journal of Physics 8 article, the title of that is What is Spin? And it has really explained the conceivable
Idea.
concept of spin, and it has also shown spin half how it has arrived, spin 1 for photon how it has arrived, mathematically also.
We don't conclude the moment. When we go through the dimensions, we have certain points or certain proofs कि multiverse जैसा कुछ exist करता है. So.
No. See, we still have not. See, these are all ideas. Okay, how will you say that?
I think it is little out of this topic is little out of, but that we can have some discussion later on. So why to keep the second lecture, because this is not directly related to the talk which he has delivered, right? We can have discussion during the times, whenever.
Okay.
Charge is an intrinsic property, my vice system. Charge is an intrinsic property. Similarly, if you go in particle physics, they call it strangeness, value of number, electronic number. These are all intrinsic property, which is a kind of a means nature. Nature carries all these things. You cannot say that why the charge is this. So this is another in the particle physics at this level, micro level. These are all intrinsic property because we are not able to understand what is going on. So we have imposed on them this intrinsic property. Otherwise there may be, I don't know, what is a strangeness? What is a periodic number?
I will ask what we attributes.
I can't use it.
And another one which is called certain internal attributes, right? The spiritual thinking, your way it is being driven, your actions and reactions, and then your interaction with the society, to your colleague, to your everyone in the universe is being controlled, is being guided by those principles and characters and attributes that you possess. And such, each particles also possess such intrinsic attributes. And spin may be one of such attributes that particle will have. Other things are you read physics, spin, that will know.
Okay.